Hello and welcome once again for another ES340 example problem video. This time we'll be discussing something related to the TDS equations. So a system containing 2 kilograms of water, initially at 160 degrees Celsius and 10 bars, undergoes an internally reversible isothermal expansion during which there is energy transferred by heat into the system. We're going to obviously into means that it's positive, using our standard way of looking at things from the textbook of 2,700 kilojoules. Determine the final pressure in bar and the work in kilojoules. Okay, so we know that we're actually given some mass here. M is equal, lowercase m, is equal to 2 kilograms. We know T1 is equal to 160 degrees Celsius. P1 is equal to 10 bar. And it undergoes an internally reversible, isothermal expansion, which means that T2 has to be equal to T1, right? Isothermal. But there is some kind of change, right? It was an internally reversible expansion. So the volume is going to change, and so is the pressure. So how are we going to deal with this? Well, the first thing is that we're going to note that the entropy is going to change. And our TDS equations say the following. Remember, we had a TDS equation that looked something like this. We didn't call it TDS yet in this format, but that basically means that T times ds, this is capital S now, be careful. This is not lowercase s. This is not specific entropy. Is equal to dq, assuming internally reversible. Okay, so if I integrate both sides, what I find is T times S2 minus S1, these are capital S's, again, still capital S's, is going to be equal to the Q of the internally reversible process. In this case, there's only one heat. If there were multiple, it would have been, Q1 and plus Q2 plus whatever, going around the boundary. Remember how we did those? We've done problems like that at this point where we sum around the boundary or whatever. But in this case, there's only one heat that's given in the problem, right? So we don't have to worry about doing a sum. It's just one value in this case. Okay, now we were given M, so that's going to be helpful for us. And the reason is basically note that S is equal to M times lowercase s, right? So if we do that, we can say T times M now, lowercase s2 minus s1 is equal to the Q internally reversible. We can actually find the value of S1, lowercase s1. Basically, if you look at these values here, the 160 and a pressure of 10 bars, 160 Celsius and a pressure of 10 bars going to the table A2, what you'll find is that this is in the compressed region. And so because it's in the compressed region, we'll say that S1 is approximately equal to the SF value at T equal to 160 degrees Celsius. And so SF is equal to, let me just write it as S1 now. S1 will take to be equal to 1.9427 kilojoules per kilogram Kelvin. So basically, we took the liquid value, the saturated liquid value, because it's in the compressed region, and we can make that approximation. We're not at super insane pressures. We're at a high pressure, but not super insane pressures or anything. So we can still view this as being in the incompressible regime. So this is definitely liquid water we're dealing with here. And so then we can obviously solve, if we wish, for S2. I'm going to solve this equation up here. Solve that for S2. So it's equal to S1 plus Q of the internally reversible process divided by M times T. And then that's going to be equal to, well, we had that S1, 1.9427 kilojoules per kilogram times Kelvin, plus 2,700 kilojoules. That was the Q that we were given in the problem, divided by the M, which was 2 kilograms. And we have to convert to, remember, we always convert to Kelvin, and the conversion to Kelvin just makes this 433 Kelvin. I'm dropping the 0.15, right? I'm not going to worry too much about the slight change that makes. So what we find is 5.0605 kilojoules per kilogram times Kelvin. So that's what I got for my S2, but that doesn't help me per se, because I want to find the final pressure, so P2, and I also want to find the work. Now, what we're gonna use is the energy balance equation in this case, right? Delta E has to be equal to Q minus W plus delta U plus delta KE plus delta PE. This is going a little bit further back, because remember, we were dealing with, this is a closed system, by the way. We were dealing before we started entropy. We were and the second law. We were dealing with systems that were control volumes, which has a slightly different equation than this. But you should remember this equation from a while back. So that's that is my energy balance equation. I'm sorry, here I made one slight mistake. This is going to be equal to, not plus. Sorry, equal to, there we go. So the delta E is equal to Q minus W, equal to delta U plus delta KE plus delta PE, okay? So that means Q minus W has to be equal to, well, in this case, notice I'm going to drop some of those terms, because notice that that I don't have any information that would tell me what the change in height would be in this case, or of the mass of water, or anything that indicates to me the velocities. So I can ignore those terms that are related to that, which would be the kinetic energy and the potential energy terms. So this is just going to mean that W is going to be equal, if I move W over, is going to be equal to Q minus delta U. Or let's write it out more explicitly, capital U2 minus capital U1. Okay? So I have S2, I have this equation, and basically what I'm going to then want to find is the values of U1 and U2. And so I'm going to make a note about what S2 is in a moment here. but I'm going to want to find but remember on the tables that I can rewrite this, by the way, as Q plus U1 minus U2 if I want. Doesn't matter. These are uppercase. Sorry. Uppercase. But remember on the table I'm given specific values. So U is equal to lower m times lowercase u. So that's going to be equal to, the work is going to be equal to Q plus m times lowercase u1 minus lowercase u2. You see I just distributed that negative sign through from here to here. Okay, so that's going to be my work, and obviously I'll be able to find the pressure as well now because I have S2 value. I'm going to do one more thing. I'm going to find U1. Remember what we said. This is from table A2. We said for above, we're going to use the same justification that S is going to be approximately equal to SF. So U1 is going to be approximately equal to UF, because again, it's in the compressed region in the first state. So this value is going to be given by, reading off the table here, 674.86 kilojoules per kilogram. Okay, and that's my U1. Now S2 is a mixture, indicates a mixture, sorry. It's in between at T2, which is 160 degrees Celsius. The value that we get for S2 ends up being, at that temperature, at 160 degrees Celsius, ends up being a mixture. So since that is the case, we're going to have to find the quality. So let's do that. X is going to be equal to S2 minus SF over, which is the F being the one that the S2 value comes from, basically, over SG minus SF. So it'll be in the same, it'll be still at temperature equal to 160, right, is what I'm trying to say. So that's the SF at 160, SG at 160, and SF at 160, okay? So there's my quality. And what I find is if I plug in the values off the table, it's 5.0605 minus 1.9427 over 6.75. This is the value off the table there, minus 1.9427. And that's going to be approximately equal to 0.649. That's my quality. And since this is a mixture, then we just use the saturation pressure. 6.178 bar. I can just read that right off the table. This is a mixture, so again, remind yourself of how you use the tables, but the pressure is constant when we're moving from a saturated liquid to a saturated vapor. The pressure doesn't change, so there's a saturation pressure. We use that when it's a mixture. And then finally, we need U2, and the reason we need U2 is to find W, which was part of the problem here, which is why we have this equation. So what is U2? Well, U2 is going to be equal to UF. Again, this is at a temperature of 160. UF plus that X value that we just found, UG minus UF. And that's going to be equal to 674.86 plus 0.649 times 2568.4 minus 674.86. That gives me about 1903.77 kilojoules per kilogram. So finally, W is going to be equal to 2,700 kilojoules. That was my Q, right? That was this. Plus 2 kilograms times the U1 minus U2, because we determined that was the equation here in this particular case using the energy balance equation. So that's going to give me 674.86 minus 1903.77 kilojoules per kilogram. Obviously, the kilograms are going to cancel that out, and that gives me about 242.2 kilojoules. And because the value is positive, indicates, since it's a positive value, work is going out. Okay, that's based on our understanding from the textbook for what positive work means. That's all that I have for this video. Hope to see you again soon.